Alright, section 8.6 deals with alternating series and absolute and conditional convergence. First I'm going to talk about alternating series. Alternating series looks like something like this, where we have alternating. The alternating, of course, and you know this, refers to the, let me write out a few more terms here. So this looks a little bit like a harmonic series, but you notice we have a plus sign alternating with a minus, plus, minus, plus, just perfectly down the line, plus, minus, plus, minus, plus, minus. That's what they mean by alternating. It's the signs that are alternating from positive to negative. And you recognize this as a little formula when you see something like -1 raised to the n power, or -1, sometimes it's going to be raised to the n plus 1. If it's n plus 1, then and n is equal to 1, that means the first term will be positive. If n is equal to 1 and it's just n, the first term is going to be negative, and that's the only difference between those. I didn't mean to make this look like a ratio or something. It's just what you're going to see. And for instance, how would we represent this harmonic series that's now an alternating series? It would just be, we'd take our harmonic series formula, which is just that, and we'd stick out in front of it a -1, and we're going to raise it to a power. We want the first term to be positive, so we're going to use n plus 1, and that's going to work out because n plus 1, n is equal to 1, plus 1 is 2, -1 squared is 1, therefore it's positive, and then we're off to the races, and that alternates positive and negative. It turns out that working with alternating series to test for convergence is pretty easy, actually. And if you look at in the book Theorem 14, it explains what has to be satisfied to prove that a alternating series is convergent. Okay, so this is a test for convergence. Number one, they say that if you have an alternating series of the form u1 minus u2 plus u3 minus u4 dot 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 dot, it says that all u sub n's are positive. Yeah, that's true, but what that really is saying, that it's an alternating series, because if we came along here and say u3 was negative, then now this becomes a minus sign, and it's no longer an alternating series, it's something else. We have to have that perfect alternation. So in a way, this first point in Theorem 14 just says, yeah, and it's a real alternating series. Accept it. That's important. To apply the alternating series test, you need to have an alternating series. Okay. 2. U sub n in our series has got to be greater than or equal to u sub n plus 1, at least after n is greater than some arbitrary number n. Okay? And what this says, basically, what they're getting at here is that eventually, you know, as n goes to infinity, you have to be in a situation where the nth term is going to be bigger than the nth plus 1. In other words, the function is decreasing ultimately. Now initially, if you had a function that kind of looked like this, there's initially it goes up and then it goes down forever. Okay, you're okay. That's going to work. That satisfies this, because here we have a value of n, and value of n, and after that everything's decreasing. Now how are you going to know this? Okay, how are you going to be able to prove that that is indeed true for a particular series? Obviously what you're going to do there is use the first derivative test, and you want to show that after some critical value n, or maybe everywhere, who knows, that the first derivative is negative. So you may have to do a first derivative test. But that should be fairly easy. And then third, and the final thing that you have to be able to show, is that as a limit, as n goes to infinity, u sub n is going to 0. Now this is one of those things that a lot of people try to say, if this is true for a regular series, not an alternating series, but a regular series, then it must go to 0. But we know from experience that 1 over n, the series, the harmonic series, does not converge, and yet it does go to 0. However, if we have this situation up here, an alternating series, you know, that looks a little bit like a harmonic series, it does go to 0. The nth term is indeed larger than the nth plus 1 term, and it converges. Okay, so if these three rules or conditions are met, and really it comes down to these two, because the first one is just, it is indeed an alternating series. If these two conditions are met, you're done. In fact, I probably would say the first thing I would do is look at the limit and make sure that this sequence is going to 0. And if that's true, then look at your first derivative and prove that it's negative ultimately. And then you know you've got a convergent series. And that is all there is to that.